All right, let's take a look at today's lesson. So we're starting out with, we're actually going in order of College Board, the way that they have their account set up. This is the first topic in the sequence that College Board puts out for AB Calculus. And we're going to talk about the average rate of change. It's just an idea of limits. We'll get more into limits in the next lesson, but this is just an idea of limits. So you probably remember from last year, hopefully, the average rate of change formula, the f of b minus f of a over b minus a. That's really just, what are we doing? We're really just finding slope of the secant. I mean, that's really what it is. It's just finding slope of the secant. That's what that formula does for us. So that's kind of tying it back to what we learned last year, that we're using this formula to do slope of the secant. We're taking a little bit of a step further. So let's look at right here. So this green line is the secant. And you can see, here's our little formula for this slope of the secant business. Okay, so that's it. So basically a change in y over change in x. This is where we were last year. We're going to take it a step further, and we're going to talk about the instantaneous rate of change, or instantaneous velocity. This instantaneous velocity and slope of the tangent line is instantaneous velocity. These are basically represent the same number. Those are the same number. So I'm just going to write that out. These are the same number. So the slope of the tangent line would be the same as the instantaneous velocity at that point in time. So those are the same. And this is the formula that we use right here to calculate the instantaneous velocity or slope of the tangent line. So let me write a little note here. This is called the alternative form of the definition of the derivative. Now, we're just doing big picture things today. We're not going to actually use this formula to calculate the alternative form of the definition of the derivative. I just need you to see where we're going. So this is kind of like just a preliminary lesson explaining what we're getting ready to be working on. So it's the background, it's the big picture. So this is called the alternative form of the definition of the derivative, and it will be on, a formula quiz. It'll say alternative form definition of the derivative. You write this formula down. That's the way it will appear. So here are two different visual representations of instantaneous velocity and the slope of the tangent line. So if we were to, and again, we're not doing these kind of limits today, but if we were to take the limit of, let me just make this a little bit bigger. So this S, and maybe you remember this, I bet they use this in physics. I'm pretty sure they do. Like S of t is a position. That's a position function. So what they're doing is the limit as t goes to 1 of s of t minus s of 1 over t minus 1. That's a calculation that we will learn how to do. And in this particular scenario, they got 64 feet per second using the formula. So that is one way to calculate the instantaneous velocity, also known as, well, this is instantaneous velocity or slope of the tangent line. Let's look and see how that relates. If we go over here, so this function, first of all, I want to pause here for a second. I don't want to go too fast. Is everybody okay? Okay, we're good. All right, so on this other little slide, we can see that this right here, the black curve, that's S of t. Okay, that's the position function. That's a graph of the position function. And the red line is a tangent line. So this is a tangent line. And what is happening here is the slope of this tangent line is actually 64. If we were to find a way to calculate the slope, we had 2 points, you can find the slope given 2 points on a line. We have 2 points in the line, and we calculate the slope, we would get 64. So this is really just a visual representation that they are the same number, but we get them different ways. Right? On the left side, that's an actual limit that we're going to calculate in the future. On the right side, that's just the slope of a tangent line that we could calculate. Really now, if we had the points, we could calculate that now. Okay, so I'm going to pause here for a second. Is everybody okay so far? Okay. So how are we going to see that with problems? I have 2 pages of problems. So let's look and see how we see that with problems. This is where our calculator comes in handy. It comes in handy. So let me... So if you have your calculator, that would be handy if you'd get that out. Don't y'all just love technology and how maddening it can be? Sorry, I'll calm down. All right. I know. Look at all this. Okay, so here we go. So what they want us to do, let's just kind of read through our instructions. Words are important in calculus. I know, it's like calculus. Yeah, words are very important. So this table gives us the position of an object moving along a line at time t over a 2-second interval. Okay. Find the average velocity. So when we hear this, average velocity, we need to think this is a formula. And the average velocity, if it's the average rate of change, we'll just use function notation, f of b minus f of a over b minus a. Okay, so what we need to start doing is attaching words to formulas. Because when the words appear in the problem, that means we're going to need to use that formula. And if you don't know the formula, you can't do the work. You see what I'm saying? How formulas are important. You have to know them. All right. So this particular problem, they want us to find the average velocity, which is this formula right here, which is average rate of change of the object, and they want us to do it twice. Okay, that's fine. So let's see. So they use S. So it would be S of, and I would use 1.5 minus S of 0 over 1.5 minus 0. Okay, so now putting numbers into it, let's see. S of 1.5 is 66. So 66 minus S of 0 happens to be 0 over 1.5. Now, this is just a pretty straightforward calculation in your calculator, so I'll just, save you the trouble. I already did put this in my calculator. 66 divided by 1.5 is 44. And since this is a rate, we would usually do units, which we don't have here, so units per second. Now, since they don't give us the units, you don't really have to write that. I just want us to, know that usually we always would want to write units with our numbers. All right, is everybody okay? Okay, so the next one, same scenario. We're going to do our, formula. So this would be S of 2 minus S of 0.5 over 2 minus 0.5. And let's look up at our chart. Let's see. So S of 2 is right here. That was 72 minus S of 0.5 was right here. That's 30 over, let's see, 2. I'm not going to trust my arithmetic. I'm just going to write 2 minus a half. And again, I went ahead and put that in my calculator, and that yielded 28 units per second. So this actually should be reminiscent from last year. We did some of these problems last year. Do y'all remember these, doing the average rate of change problems, or no? It's like a blur. Some yes, some no. That's okay. It's fine. All right, so that's the first kind of problem that we will encounter. Any questions? Okay. So the next one is really more of the same. Okay, it's more of the same. So they give us a position of S of t of an object moving along a line at time t. Determine the average velocities over those three time intervals. And then they want us to make a conjecture about the value of the instantaneous velocity at 1. Okay, well, we can do that. Now, where's my big, gigantic pink cursor? It's gone. Okay, we won't. All right, so here we go. So let's do it's the same formula. It's the average rate of change formula. Oh, I know the problem. God, I'm such a goofball. Okay, so same formula as up here. So we've got, and let's do this one first. This is our first one, number 1. So we have S of 1.01 minus S of 1 over 1.01 minus 1. So that is, I'm just going to pull the numbers off of my table. That's right here. There's my 1.01 is 64.4784 minus S of 1, which is right here, is 64 over 0.01. And again, I went ahead and put it in my calculator just to save you the trouble. We are going to use our calculator. I'm going to show you something on the next page. But for here, it's just really simple calculations. We should be pretty good with that. This gives me 47.84. Does anybody remember from last year, what is our default rounding? What is our default? Thousands. It's thousands. We should always round to the thousands unless there's a reason not to. Okay. Anybody think of a reason not to round to the thousands? Dollars? Yeah, on dollars we wouldn't round to the thousands unless we're at the gas station, right? We don't want to do that. So what's another reason why we would never round or put it to the thousands? Yeah, like a person. You really don't want to say there's like a half a person. That's not okay, right? That's not okay. So we would just go maybe round up or round down, whichever way we wanted to do. So otherwise, if it's not one of those two scenarios, you need to round to the thousands. Okay, here we go. So the next one is we need to do S of 1.001 minus S of 1 over 1.001 minus 1. Okay, so that's our next. We're doing number 2. All right, so we've got 64.047984, where they like to give us lots of decimal places, minus 64 over, what is it, 1.00. Well, I'll go ahead and subtract. That's not too hard. So 0.001. Again, I put it in my calculator. This is a fairly simple computation in my calculator, 47.984. So I want to talk about this for just a minute. This seems kind of weird, don't y'all think? I can't leave my recording. So I'm starting out at 1.01 to 1. So let's think about what's happening. Okay, so we'll just do a number line. Why not? So here's 0, and there's 1, and there's 2. Okay, so 1, we know where 1 is. 1's right here. What about 1.01? Isn't that pretty close? That's pretty close, isn't it? That's like right, like there. And what about 1.001? That's even closer. So it's even closer. And then 1.001 is even closer. So I need us to understand what's happening. what's happening is we're calculating slopes of secants that are getting smaller and smaller, like closer together. Okay, that's how we're going to make our conjecture, because the limit is all the way, like, it's the limit of all of those together, which you're all like, God, what is that? You're driving us crazy. That's okay. We're going to do lots of limits. So we're getting closer and closer to 1. Just keep that in mind. We're getting closer and closer to 1, which is a good thing. So the last scenario is S of 1.0001 minus S of 1 over 1.0001 minus 1, which, just writing the numbers off my table, is 64.00479984 minus 64 over 0.0001. And again, putting it in my calculator, I've got 47.9984. So the question we want to ask ourselves is, as we get closer and closer to 1, now we're going from 1 to something on the right, 1 to 1.01, 1 to 1.001, getting closer, what's happening to our answer? Is it getting closer to a particular number? It's getting closer to 48. So that's what we would write our conjecture about. So our conjecture would be, and I'll just write it out kind of, since the values of the average rate of change as t gets closer to 1 are getting closer to 48. So the instantaneous velocity at t equals 1 would be approximately 48. So what am I doing? I'm explaining how I know that. We've just noticed that the values of the average rate of change as t gets closer to 1 are getting closer to 48. So therefore, the instantaneous velocity at t equals 1 should be about 48. That's our conjecture. Okay, so I'm going to pause here for a second. How are we doing? Everybody okay? Okay. I'll wait here for just a moment and make sure we're all together. We've got a couple of problems on the second page, and then the lesson is, done. Darn. I just want it to go on and on, right? Sorry, I know, right? It's so fun. So fun. Okay. So this problem, I will just tell you, this problem came out of AP Classroom. This is actually one, you're going to have a problem almost exactly like this in your AP Classroom little thing that we assigned you. Almost exactly like this. So we're doing one together so that it'll make the one that you do on that APC easier. Okay, so here we go. Let's see what we got going on. The size of a population of bacteria is modeled by the function p, where p of t gives the number of bacteria. Okay, and t gives the number of hours after midnight. So I like to mark this up. We won't have highlighters, but we certainly can underline stuff. So p gives the number of bacteria, and t gives the number of hours after midnight. That's important information. The graph of the function p and the line tangent to p at t equals 8 are shown above. Which of the following gives the best estimate for the instantaneous rate of change at 8? Okay, so let's look at our scenario here. So P of 8 is like this number right here. Okay. Now, they want estimate for instantaneous rate of change. is that, so that's going to be the slope of that line. Are you with me? Instantaneous rate of change is going to be the slope of, so let's just write this out here so we remember. So slope of the tangent line equals instantaneous rate of change. Now this number of, whatever this is, like 6,000 or something, that's not that slope. So that first answer, so again, slope of the tangent line equals instantaneous rate of change. They're the same. And that first option is not good. So we know it's slope, right? Slope of the tangent line is equal to instantaneous rate of change. So let's look at these other three scenarios. We want the slope of the line, so I'll just change colors. So we'll do a different color for each one. So this one is going to be pink. So we're going to 0p of 0, so that's right here. And 8p of 8, 8p of 8 would be right here. So that slope. Does that look like a good estimate, that slope? Does that look like a good estimate of that tangent line that's drawn? Not really, does it? No, it's not as steep. I'm not liking that. Okay, let's change colors. Let's go to this one. So now we're going to go 0p of 0 to 10p of 10. So we're up here. So it's this slope. Does that slope look like a good option for us? I mean, it's a little better, but is it really good? Not really. Not really. Okay, so let's look at our last option. Let's hope that's the right one. We'll go with purple. So 7.9, p of 7.9. So that would be like here. 7.9 p of 7.9 and 8.1 p of 8.1. That would be like right here. And if I draw a line between them, okay, does that look pretty good? That looks pretty good, doesn't it? So that would be, so the purple one is the one that really most closely matches. So we would circle D, or in the computer, you just click D. And that's really the best option for us. Does everybody understand why?
Yes.
Okay, perfect. And so you can see why some of those really aren't really good, because why? Why is this one better than the others? Exactly, because it's closest to that point. We want to know the rate of change at 8. Well, 7.9 and 8.1 are really close to 8. So that's really a good estimate. 0 and 10 and 0 and 8 aren't really close to 8. Does that make sense? Okay, so that is how that kind of problem works. Now this one, number 4, is the one that I want us to use a calculator on. This is the one where I'm going to show you, you probably remember from last year or the year before, but this is a very beneficial technique for you to use, especially like on the practice we're getting ready to do. There's some problems that this would really help you out. So what is this wanting us to do? They're giving us a position function, and they want us to find the average velocity. So I'm going to write the word out. So they want the average velocity. So they want s of 2 minus s of 1 over 2 minus 1. I mean, that 2 minus 1. And I'm going to circle average velocity, and I'm going to write, that's a formula. I'm going to write out the formula. F of b minus f of a over b minus a. So when I write on your formula quiz average velocity, we should have that, right? F of b minus f of a over b minus a. That's what it is. Okay. So yes, let's just say outside of this, how would we find s of 2? Can somebody tell me how would we find s of 2?
You would plug in 2 for t.
Exactly. That's what I would do. I would plug in 2. I would say negative 8 times 2 squared plus 7 times 2. That would be a lot of work, right? But I could do it. I could do it. So that's just where the calculator comes in quite handy. Okay? So let's go to the calculator and I will show you, especially if we have more than one to find, because, you know, on your practice we do. Yes, ma'am.
My calculator is like locked.
Oh, like the,
It says CAS off, and there's a lock.
oh, yeah, I can undo it when we start. I can undo it for you. I'd have to hook my calculator to yours. It would take a second, but I could undo it for you. Okay, so let's go to our calculators. And what I'm going to do is I'm going to, and let me go over here real quick so I can see it as I'm working it. Okay. All right, so let's get our calculator, and I'm going to go to the grapher. I'm going to add a document. I'm going to add a graph. And in the grapher, I'm using the grapher to store my formula. Okay, let me make this big. So I'm going to store, and that formula was what? Negative 8x, and I don't use the t, just use x. X, come on, you can do it, squared. And then, what was it? It was plus 7x. And then just hit enter. Okay. Now I just stored it there. I'm not going to really use that graph. Okay. Now I'm going to do another page. Y'all remember how to do that. So Control Doc. And I'm going to put a calculator on this page. And what I'm going to do is I'm going to actually basically mimic that formula. I'm going to do my fraction deal, which is Control Divide. I love that little fraction thing. Do y'all use that? Oh my gosh, it's best. It's the best. Okay, so there's my little fraction. Are we okay? Yes, Control Divide.
I forgot. How do you copy?
I can't copy. I don't know.
Okay.
I don't know how to copy. We'll figure it out, but yes. Really? Control plus page? So maybe we need to update the operating system after we're done. I know Mr. Lancaster has that thing that can update it. Yeah, I'm sorry. I don't know how to add a doc unless do Control page. I know there's another way.
Control doc.
Control doc?
Yeah, it's like the plus page is flashing.
It's not working? Okay. So when we have this, okay, so everybody, well, those of you that can get to this extra page, can you get here? Here, you want to use, just leave your font here. You can use this one. This one should work. Thank you. You're welcome. All right, so here's the great part. I'm going to see this VAR button right here that's in red. See the VAR? See the F1? That's where we stored that function. So VAR, I want to hit F1. See how it just came up there? We're just going to type it in. So that's basically S of 2, right? And then minus. And then we're going to hit that VAR button again. Hit the VAR. See it in red right there? That VAR button, like by the little cursor dealy. And then click on that. And so F of 2 minus F of 1. And then that's over 2 minus 1. And I really don't try to do any arithmetic in my head. It doesn't work well for me. I'm just going to let the calculator do it all. So is everybody okay so far? And then we just hit enter. And then there's our answer. Now this is really handy when you have a bunch of them defined. And now that kind of copying I do know how to do, dear. So what we would do is we would scroll up right there and then hit enter. So if you highlight that and hit enter, it brings that whole thing down and you can just go in and change the numbers. That's what will be very helpful, especially on the practice. Okay, so is everybody okay with the calculator? Yes? All right, so our answer is negative 17. So let's see, so it's negative 17 and they didn't give us any units, so we can just stop with that. All right.